Okay, so we solved a completely decoupled system, right? Each derivative only depended on its own variable. Now we'll look at a partially decoupled system, which again is kind of about what you might think. So if I ask you to solve this differential equation, dx dt equals 2x plus 3y, and dy dt is negative 4y, and I tell you that x of 0 equals 0, y of 0 equals 1. This is what's known as a partially decoupled system, right? Because the derivative of y only depends on itself. X will depend on both. What do you think you do when you're solving a system like this? Well, we can solve this for y. And if we know y, we can use that to find what x is, right? So that's exactly what we're going to do. So again, I highly recommend you pause the video, do this all out. I will also quickly, and I say quickly, go through the solution myself so you can see some steps without having to just check your answer only. So if we solve y first, right? If we solve y first, what do we get? We get that y of t is any constant. Let's use k1 because we have two things here. We have two constants. K1 e to the negative 4t. Okay, that's, is a very basic. The derivative is proportional with a decay constant of the thing. And again, we know that y of 0 equals 1. Oh, okay. So k1 equals 1. Great. So that's part of our solution. And now, right, we go over to number 2, and we try to find what dx dt is. So dx dt is 2 times x plus 3 times y. And again, y is equal to this. Now we have a linear with constant coefficients, non-homogeneous, first order differential equation. It is not autonomous, it depends on t. We can use an integrating factor here. We could use the guess and test method with the linearity principle. We could find the homogeneous solution, right? That's going to be e to the 2t. So the homogeneous solution. And then, let's just do that, right? Not yh, right? Xh. That's going to be pretty simple. It's just going to be some constant times e to the 2t. And then we have to say, okay, well, how can we kind of guess a particular solution so that this is the case? All right. Actually, I really hate this method. I should have just done integrating factors. So, right, what do we have? We have dx dt minus 2 times that x needs to equal 3e to the negative 4t. What form do you think our answer is going to be? Our answer is going to be in the form of some constant times e to the negative 4t. That's what it has to be for this to work out. So then what we can do, right, is just take the derivative of this. We'll get negative 4 alpha e to the negative 4t minus 2 times that needs to equal 3 times this. And of course, they all have e to the negative 4t's, and that will never equal 0. So really, all we have to do is find out when is negative 4 alpha minus 2 alpha equals 3. Negative 6 alpha equals 3. Alpha is negative 1/2. And we find our particular solution is going to be negative 1/2 e to the negative 4t. And what we get our homogeneous, we get our particular. We can combine that into our x of t. Actually, let me write it over here next to our y. X of t is our homogeneous, c e to the 2t, plus our particular, 1/2 e to the negative 4t. And again, x of 0 is equal to 0. You plug in 0 here, you get c minus 1/2. I think c is 1/2. All right. So one last double check, right? T equals 0, we get 1/2 minus 1/2. That needs to equal 0. Okay, we have our solution. That's it. All right. So again, let's do some quick analysis. See what we have right here. Let's look at the direction field or the vector field, depending on what I feel like drawing at the moment. And again, we'll switch over here so you can see it better. 2 times x plus 3 times y. Again, this plotter does require that you write out the multiplication. And this is negative 4 times y. Ooh, that looks interesting. Again, gets kind of hard to read with a vector field sometimes. So let's make it into a direction field. Now we can see a little bit more what is happening right here. And specifically, our initial condition was that x was initially 0 and y was initially 1. So this was our initial condition. So you can see that as time passes, x is continuing, but y is going off to 0. And again, we can compare that with our, oh dear, something. There we go. We can compare this with our solutions, right? We can graph our solutions. We said that we had, I already forgot. We said x was 1/2 e to the 2t minus 1/2 e raised to the negative 4t. That is what we had, right? Great, we did. And we said our y coordinate was just e raised to the negative 4t. So now we can see a somewhat more interesting graph than in the last one, what x is doing and what y is doing. Y, we're going to have to zoom out a little bit, right? So as time passes, again, x is starting off. Oh, wait, this is y. Wait. Yeah, x is the messier one. X is red. All right, y is starting off at 1, and x is starting off at 0, just like we wanted. But as time passes, y is going to 0, and x is going off to infinity. Isn't that exactly what we said should happen? As time passes, x is going to infinity, and y is going to 0. This is the xy plane. Whereas here, we're graphing x and y individually over time. Okay? All right. Again, very important to be able to compare and contrast these two solutions. So I have a question, is what happens if we start with an x value of -1/2 and a y value of +1? What happens? Something very interesting happens if we start here. What about with an x value of +1/2 and a y value of -1? We get essentially there's like a straight line right here, depending on your initial condition. That straight line is going to be very, very meaningful, and we're going to talk about where that straight line comes from in Chapter 3. We've actually seen it already in a previous section in Chapter 2, and it's going to have to do with eigenvalues and eigenvectors, and it is going to be a big part of looking at linear systems with constant coefficients. Because if you notice, right, this is a linear system with constant coefficients. We haven't introduced exactly what that terminology means for systems of differential equations yet, but hopefully it's not a crazy claim to make. So we got some exciting things coming up. This is the end of Chapter 2. We get into Chapter 3 next. We're going to see how do we find these special line solutions, how do we look at other curve solutions, and y'all are in for a treat. But that's it for today. Bye-bye.